So coming to the first question, LO is the training objective in VAs and it balances two parts. How well the model reconstructs the data and how close the latent distribution is to the prior. So it's a trade-off between accuracy and generalization. So in diffusion models, it is a similar idea we keep using, but instead of the latent space, we model the reverse of a noise process. So the elbow here helps us to train a model that learns how to de-noise step by step and reconstruct the data from pure noise. So in both cases, elbow helps us to train the models that can generate realistic data while also maintaining the structure in what they learn. So that's the main reason why elbow is used in both VAs as well as diffusion models. And now coming to the beta VAE objective and the role of beta. So beta VAE is like the modified VAE where we multiply the KL divergence term by a factor beta uh, uh, in the elbow. So this lets us control the trade-off between a reconstruction and how disentangled the latent variables are. So a higher beta encourages more independent and interpretable latent features, but can reduce output quality. But at the same time, a lower beta gives reconstructions, but it provides also an entangled representations. So beta helps us to decide whether we want to have clarity in the latent space or better image quality. And that's about the beta part. So coming to diffusion process and data generation. In diffusion models, the core idea is to gradually turn real data into random noise through forward process in the encoder, and then to learn to reverse this transformation by step using Markov property. So during training, we teach the model how to denoise the data from each noisy state and back to the original. So mathematically, each step adds a small amount of Gaussian noise, and the model learns the reverse of this process. At inference time, we start from pure noise and apply learned steps to generate new samples that resemble our real data. This makes diffusion models powerful for generating like high quality images because they model the full data distribution and use gradual fine grained approach for generation. And this is why generally diffusion models are slower because there are multiple steps that keep happening. So coming to the loss function in Gaussian VAE, a Gaussian VAE has two key components in its loss function. The first is the reconstruction error, which measures how well the decoded output matches the original input. And it's usually done using a mean squared error or binary cross entropy. The second term is basically the KL divergence, which is the KL divergence between the approximate posterior and the standard normal prior, which acts as a regularizer. The KL term encourages the latent space to be smooth and consistent, helping the model to generalize better. So together, the loss ensures that the model learns useful compressed representations and at the same time being able to accurately reconstruct the output. So the reparameterization trick plays a major role in this whole process of the VAs. So the reparameterization trick is generally used in VAs to make sampling from a probability distribution differentiable because it's normally directly not differentiable. So instead of sampling Z directly from distribution with mean and variance, we rewrite it as Z equals mu plus sigma some noise epsilon, and this makes Z a deterministic function of the model parameters and random noise, which usually allows the gradient to flow through Z during training. Without this trickle back propagation wouldn't work because you can't differentiate through a sample uh, because through a sampling operation. So it's essential for training VAs from end to end using gradient descent. So that's all. Thank you.